Welcome to part 2. Before we get started, I have to address a mistake in the first video which was kindly pointed out to me in the comments by Minirop. The CPU register struct should of course contain unions containing a struct of two 8-bit unsigned integers as well as a 16-bit unsigned integer. Here's what they look like when they are fixed. And just in case it's not obvious why we want this, I can show a quick example. This setup allows us to easily set the values of the individual bytes in a 16-bit register. For instance, setting the value of register B to BB and C to CC, and then reading out the 16-bit value of the full BC register should show BBCC. It also allows us to set the 16-bit values of the registers, like for instance setting the value DDEE to the DE register, and then reading out the individual 8-bit values of registers D and E, which will hold the values DD and EE respectively. This is useful as we need to read from and write to these registers in both ways, so it saves us having to do a bunch of bit manipulation within the instructions themselves. Thanks again to Minirop for the comment, and if any of you notice any other mistakes along the way, please do point it out in the comment section. Speaking of comments, I just want to say thank you for all the kind words, and to let you know I read every single comment and appreciate you taking the time to write a few words. In an attempt to increase the quality, I did the last video in 1440p, but I feel like it just makes the text harder to read, so I've switched back to 1080p instead. Let me know which one you prefer in the comments below. Right, with all that out of the way, let's get to it. In the first episode, we covered these 8 CPU instructions, which we got to by repeatedly trying to run Tetris and stopping whenever we hit a new instruction. If your goal is just to run Tetris, I suggest you keep doing this until you have covered all the instructions. In total, you will need to implement these 130 regular instructions, as well as these 2 CB prefixed instructions. In this video, we will switch gears a little, as I'm assuming most of you watching this actually want an emulator which can play more than just the one game. To that effect, we'll try to go through all of the remaining instructions in a slightly more efficient way. Let's get started. We already wrote a few routines which we can use to implement multiple instructions. The first one of these is the 8-bit register immediate load, so let's implement the rest of the instructions which use that routine. We already covered registers B and C with opcode bytes 06 and 0E, so we just need to add these for registers A, D, E, H, and L. These cover opcodes 3E, 16, 1E, 26, and 2E respectively. Don't forget to add them to the instructions array. Next up, we have the 16-bit loads, of which we already implemented the immediate load to register HL with opcode 21. Let's add the loads to registers BC, DE, and SP with opcodes 01, 11, and 31. We have one more routine already implemented for 8-bit decrement instructions. It was used for decrementing register B with opcode 05, so we will add the rest for registers A, C, D, E, H, and L. These cover opcodes 3D, 0D, 15, 1D, 25, and 2D respectively. Following that, we will implement a new routine for 8-bit indirect loads. This routine will load a value from an 8-bit register to the address in memory given by a 16-bit register. The routine itself is fairly simple, as it's really just writing to the memory bus, and it's used in opcode 02, 12, 70 through 75, as well as 77. The next routine will implement 8-bit indirect loads, but this time the value is loaded from the address given by a 16-bit register and stored in an 8-bit register. Once again, it's a very short routine, and it's used in opcode 0A, 1A, 7E, 46, 4E, 56, 5E, 66, and 6E. There's not much to say about these, they simply increment the value in a 16-bit register by 1. This routine will cover opcode 03, 13, 23, and 33 to increment registers BC, DE, HL, and SP. This is exactly the same as the previous routine, except of course we decrement the value by 1 instead of increasing it. Similarly, it will cover opcode 0B, 1B, 2B, and 3B to decrement registers BC, DE, HL, and SP. This is more of the same, but this time incrementing the value of 8-bit registers by 1. The routine will be used for opcodes 04, 0C, 14, 1C, 24, 2C, and 3C to increment registers B, C, D, E, H, L, and A respectively. This next routine will add the value of a 16-bit register to the HL register. The check for the half carry flag here is the only tricky bit, otherwise it should be fairly straightforward. This one covers opcodes 09, 19, and 39. Here we have a routine to add values from 8-bit registers to the A register, also known as the accumulator. Once again, the half carry flag requires some care, but the rest is simple. This one will implement opcodes 80 through 85. This one is quite similar to the previous one, but here, in addition to the value of the 8-bit register, we also add the value of the carry flag. This just means that if the carry flag is set, the result of the addition is one more than it would be with the regular add. If the carry flag is not set, then nothing extra is added. This one covers opcodes 88 through 8D. Now we have the subtraction of values from 8-bit registers from register A. Nothing of note here except of course the half carry flag, which can be tricky to get right. This routine is used to implement opcodes 90 through 95. This one is the opposite of the add with carry, this time subtracting the value of an 8-bit register plus the carry flag from the A register. By this point it should be pretty self-explanatory, apart from, as always, the half carry flag. This one will cover opcodes 98 through 9D. Here we have a routine for the bitwise AND operations with the A register. It's once again a fairly simple routine, but of note here is that the half carry flag is always set to 1 by these instructions. It's used for opcodes A0 through A5. Following that, we have a routine for bitwise exclusive OR operations with the A register. The only flag to care about here is the 0 flag, all others are switched off. This one covers the opcodes A8 through AD. By the way, I really recommend adding comments with the opcode value next to the CPU instruction implementation, as it will make it easier to jump to that instruction when debugging a particular opcode. Continuing the theme from the previous two routines, we also need a routine for bitwise OR operations with the A register. It covers opcodes B0 through B5, and there's not much else to say here really. This one is a bit different from the others so far, as it only sets values in the flags register. Basically, it will compare the value of a register with the value of the A register and sets the 0 flag to 1 if the values match. You also have to implement the carry and half carry flags for this one, but this time they are checking if the value of the A register is less than that of the register being compared. This one covers the opcodes from B8 to BD. Now we get to something a bit different, which is an unconditional call to an absolute fixed address, also known as a restart. In this case, the address depends on the opcode, so there's a fixed set of addresses these instructions will jump to. As always with these jump instructions, we store the current PC register in the stack. To be clear, it's the address immediately following the current opcode which gets stored at the address given by the SP register. The SP register then gets decremented to point at the address immediately below the one we just stored, and each of these steps takes 4 clock cycles. This routine will cover opcode C7, CF, D7, DF, E7, EF, F7, and FF, which jump to addresses 0, 08, 10, 18, 20, 28, 30, and 38 respectively. The next routine also deals with control flow, this time pushing values from the 16-bit registers to the stack. This one is somewhat similar to the previous one, except the PC register is not changed here. We just store each of the 2 bytes in the 16-bit register at the address in the SP register and decrement SP by 1 for each byte. This will cover opcodes F5, C5, D5, and E5 to push the values in the registers AF, BC, DE, and HL. As a counterpart to the push to stack instructions, we of course also have instructions to pop from the stack. This one takes the value from the address pointed to by the SP register and stores it in a 16-bit register. It does it 1 byte at a time, whilst also incrementing the SP register. The routine is used to implement opcodes F1, C1, D1, and E1 to pop values into registers AF, BC, DE, and HL respectively. Next up, we have a routine for conditional calls to an address. This one is interesting as it will take a different amount of clock cycles to execute depending on whether the condition is true or not. The address is the 16-bit operand, so we have to read it from the address of the PC register whilst also incrementing PC once for each byte. If the condition is true, we push the value of PC to the stack and set the value of PC to the given address. If the condition is false, we just increment PC twice and carry on. Note that on actual hardware, the operand address is read even when the condition is false. This routine covers opcode D4, where the condition is that the carry flag is not set, opcode DC, where the condition is that the carry flag is set, opcode C4, where the condition is that the 0 flag is not set, and finally opcode CC, where the condition is that the 0 flag is set. Here is the routine to handle the conditional returns from functions. This one will read the address stored in the stack and change the PC register to that address, but only if the condition is met. Once again, we have a set of operations which take more time to execute when the condition is true. The routine covers opcodes D0, D8, C0, and C8 for the conditions carry flag is not set, carry flag set, 0 flag not set, and 0 flag set, respectively. Alright, this next routine will handle conditional jumps. A jump will simply change the address of the PC register to the value in the operand of the instruction. This one also takes slightly longer to execute when the jump is taken, but it's fairly straightforward. This one covers opcodes D2, DA, C2, and C8 for the exact same set of conditions as the previous 2 routines. As the last routine for this episode, we cover the conditional jumps with a relative address. The relative part here means that the operand is only 1 byte, and that value is added to the current instruction address to get the new address. The thing to keep in mind here is that the operand value is treated as a signed integer, so it can jump at most to an address 127 bytes before the current one, or 128 after it. As always, it takes longer to execute the jump than to skip it if the condition is false. Since they only use a 1-byte operand, these instructions are faster than the ones with an absolute 16-bit address. This covers opcodes 30, 38, 20, and 28 for the usual set of conditions. These instructions are so simple that there's no point in writing a routine for them, but let's quickly implement them now anyway. First, we have opcodes 40 through 45, which load values to register B from registers B, C, D, E, H, and L. As the first one just loads from register B to itself, there's nothing to be done as nothing changes, but it still takes 4 cycles to execute. The others simply copy the value from a register to the B register. Finally, we have the same thing again, but loading from register A to register B, which is opcode 47. This pattern repeats itself for register C with opcodes 48 through 4D, where you read from registers B, C, D, E, H, and L, as well as opcode 4F to read from register A. Immediately following that, we have the same again, but this time loading into register D with opcodes 50 through 55, and don't forget opcode 57, which loads to D from A. Next, there are the loads to register E, which covers opcodes 58 through 5D for registers B through L, and of course 5F for register A. Once again, we repeat this for register H with opcode 60 through 65, as well as opcode 67. I assume you can see the pattern here by now, so I won't bother repeating myself other than to say that of course we have register L next with opcodes 68 through 6D, as well as 6F to load from A to L. Last but not least, we have the loads to register A, which go from opcode 78 to 7D, as well as 7F to load from A to A. As always, don't forget to register all of these functions in the instructions array. Okay, that has been quite the slog, but on the upside we have covered a lot of instructions in a relatively short amount of time. By my count, we have now implemented 187 instructions and are only missing 58 more from the first set of 256 instructions. We will implement those in the next episode, and we'll get to the second set of CB prefixed instructions after that. I should also point out that this is by no means a perfect implementation of these instructions. For instance, not all the casts are absolutely necessary, and the timing is probably wrong in many of them. The amount of clock cycles taken is right, but where the clocks are consumed might be slightly off. That being said, I'm fairly sure they are at least correct in the logical sense that they do what they should and will get you to a working emulator that plays some games. Okay, that does it for this episode. Thank you for watching, and I hope to see you on the next one. Later!